All right, let's dive right in. Today we're tackling something that sounds like it's straight out of science fiction, but it's actually one of the most fundamental truths about our universe. We're talking about the idea that, well, everything, a beam of light, a ball you throw, even you, doesn't just take a single path to get from A to B. It takes every single possible path, all at the same time.
I mean, just think about it for a second. When you toss a baseball, it follows this beautiful, clean arc, right? Seems totally obvious. Our entire experience, everything we see, tells us that things move along one and only one path. But what if all of that is just a massive illusion?
And look, you're not alone if you think that way. As the source for this explainer puts it, even after years of studying physics, he held on to this very same idea. So today, we're going to break down that misconception and try to see reality for what it actually is. It's going to get weird.
Okay, so to get our heads around this, let's start with something, well, a lot more down to earth. Let's imagine a lifeguard on a beach. He sees a swimmer in trouble. He's got to get to them as fast as humanly possible. This is actually a classic physics problem in disguise.
Now you might think the shortest path is just a straight line, right? But wait, the lifeguard can run way faster on the sand than he can swim in the water. So you have to ask yourself, what's the actually fastest way to get there?
It turns out the fastest path is not a straight line. The smartest move is to run a little farther down the beach to spend as little time as possible in the slow water. It's a trade-off, and here's the crazy part. This is exactly what light does. When a beam of light goes from air into water, it bends to take the quickest possible route.
And that's the big mystery, isn't it? A lifeguard can think, that can calculate the best path. But a photon, a little packet of light, it doesn't have a brain. How in the world does it know which of the infinite possible paths is the absolute fastest? Answering that question literally sparked a revolution.
So to find the answer, we've got to jump in a time machine and go back a bit, and you'll never guess where this story starts. Not in some high-minded theoretical debate, but with the super practical problem in 1890s Germany, trying to build better light bulbs.
See, physicists were studying the light given off by hot objects, like a light bulb filament, and they hit a brick wall. Their best theories predicted that a hot object should be blasting out an infinite amount of ultraviolet light. They called it the ultraviolet catastrophe. But of course that didn't happen. Something was deeply wrong with physics, and it took a whole series of mind-bending breakthroughs to fix it.
So, to fix this catastrophe, a physicist named Max Planck tried something totally out there. He called it an act of desperation. He said, what if energy isn't smooth and continuous? What if it only comes in little, discrete chunks? He called them quanta. And just like that, with this one wild idea, the math worked perfectly. But this is where things get really weird. Planck had to introduce a new number into physics to make his math work. This new fundamental constant, h. But when they looked at the units of h, it wasn't energy, it wasn't force. The units were joules times seconds, which happened to be the units of a very old, very weird concept from physics called action. Nobody really knew what it was, but it turned out to be a massive clue.
All right, the next piece of the puzzle came from a guy named Louis de Broglie. He had this brilliant thought. Hey, if light waves can act like particles, maybe, just maybe, particles like electrons can act like waves. And that idea, well, it changed absolutely everything. Because check this out. If an electron is a wave, it can only exist in a stable orbit around an atom if a whole number of its wavelengths fit perfectly into that orbit. It's like a guitar string that can only vibrate at certain frequencies. Any other orbit, and the wave would just cancel itself out. And just like that, you have the first physical reason why the quantum world has these weird, specific rules. And once you accept that particles are waves, the logic just keeps rolling, and it leads you somewhere incredible. Okay, we know from the double slit experiment that an electron has to go through 2 slits at once. But what if there are 3 slits? Well, it has to go through all 3. What about 1,000 slits? 1,000,000? What if you have infinite slits, which is just a solid screen? And then what if you have infinite screens between the starting point and the end point? You see where this is going? The conclusion is inescapable. To get from A to B, a particle literally has to take every possible path through space. Okay, but hold on. That creates a huge problem. If a particle really does explore every path, including absolutely insane ones that go to Jupiter and back on their way to your eyeball, then how come we only ever see it travel in a dead straight line? To figure this out, the physicist Richard Feynman gave us this amazing way to think about it. Imagine that for every single path a particle could possibly take, there's a tiny little spinning arrow, like the hand on a stopwatch.
How much that arrow spins is determined by the action of that path. And to get our final answer, all we have to do is add up all the arrows from all the paths.
Now for almost all the paths, all the wild, loopy, crazy ones, a tiny little change in the path results in a huge change in the action. That means their little arrows end up pointing in completely random directions. North, south, east, west, all over the place. And when you add up a bunch of random arrows, what do you get? Nothing. They're all just noise. They cancel each other out completely. Poof!
But right around the classical path, the one the lifeguard would take, something really special happens. In this little neighborhood of paths, small changes don't really change the action very much. And what that means is all of their little arrows end up pointing in almost the exact same direction. So they don't cancel out, they add up, they reinforce each other. And that becomes the one single reality that we actually observe.
So that perfect, predictable arc of a baseball, it's a ghost. It's an illusion. It isn't one path at all. It's the grand average of an infinite number of quantum paths all happening at once, with most of them canceling each other out, leaving behind the one that we see. The world we know is built on a foundation of canceled-out possibilities.
Okay, I know what you might be thinking. This sounds like some weird mathematical sleight of hand, right? A clever trick to make the equations work. But it's not. There is an absolutely stunning experiment that proves, for a fact, that light really is taking all those impossible paths. It goes like this. You shine a laser at the center of a mirror, and the light reflects to one spot on the wall. Simple enough. That bright spot is where all the paths from the entire mirror are constructively interfering. But then you do something clever. You take a special screen called a diffraction grating, and you use it to block out very specific parts of the mirror. You're basically stopping some of the cancellation from happening. And when you do that, bam, light suddenly appears in places on the wall that were dark before, proving that light was reflecting from parts of the mirror it was never supposed to touch.
What this really shows is that the darkness on the wall isn't empty space. It's full. It's full of countless paths of light that are all arriving and perfectly canceling each other out into nothingness. The experiment doesn't create new paths. It just reveals the contributions that were already there, hidden in the dark.
So why does all this matter? I mean, why is this so important? Because this idea, the principle of least action, is pretty much the most fundamental concept in all of modern physics. Seriously, if you ask a top-tier theoretical physicist what they do all day, they won't talk about forces like pushes and pulls. They'll tell you they're trying to find the right Lagrangian, which is just a fancy name for the recipe that calculates the action for any system. If you can find the right Lagrangian, all the laws of physics just emerge from it.
And that kind of leaves us with this final, absolutely profound thought. The hunt for a theory of everything, that grand quest of physics, isn't really about finding some new particle or force. It's about finding one master recipe, one ultimate Lagrangian, a single equation for action that, when you let every particle take every path, spits out the entire universe that we see around us.